Hello everyone, I'm Chetan Arvind Patil, Senior Staff Product Engineer at Indie Semiconductor. I'm going to moderate today's panel session and discussion on AI-driven semiconductor solution, which is sponsored by IEEE's Future Direction Committee and as part of IEEE Global Semiconductor Initiative. And I hope you will find this session very interesting. And there will be the main focus is like last 2 years we have been focusing a lot on the models, AI solution, and the discussion has also shifted on the computing part. So it has become very critical to understand how these three things interact with each other and what is the past, present, and future of this domain. And to give background on this information and this new solution in technological development, we have three esteemed guest speakers. We have Kirk Bresniker. He's a life fellow at HPE and have been working in the industry for many decades. Have been part of IEEE industry and at the advisory board. And we have Mustafa from Qualcomm. He's the director of engineering, working on system optimization and also on the IEEE on many more chapters. And then we also have a life fellow of IEEE, Dr. Paolo Gargini, and he will also give us some insights about how the AI interaction has happened from a few decades ago and today and what the future holds. So I would, without any delay, I would like to invite Kirk, you, for this talk to get started, and I will share the slide deck for you.
Thank you. All right, so thank you everyone for joining us. Again, Kirk Bresniker, I'm the Chief Architect at HPE Labs, and I'll be talking today to start off the consequences of scale. I think this is one of the most formidable things that we need to think about as an entire industry, how we achieve scale, how we achieve it sustainably, how we achieve it equitably. So we'll go in and talk about some of the scale laws and then how those then reflect into the engineering decisions we're making at every scale. And we're talking about individual features on GPUs all the way up to national energy grids. And the first thing we want to talk about when we talk about scaling of large language models is that the resources consequence are quadratic. And there's several places where this is enters. And it enters both in training and in inference. In training, every time we add 10 times the parameters into a large language model, we find that we are consuming 100 times the resources. So that first element of a quadratic scaling law in training is super important for us as we think about creating models with now at least hundreds of billions, and there certainly are efforts to create trillion weight parameter models. Every time we add that zero, we add 2 zeros to the resources. And the other element of that scaling is also on inference. When we want to use one of these models, first we have the same scaling laws as we begin to take these increasingly large workloads and spread them over dozens, if not hundreds of GPUs in order to inference over one of these large models. But also, as we increase the context window, as we provide more data into the models in order to best utilize its capabilities, we run into another quadratic scaling law. And as we increasingly use these for complex tasks, beyond just simple search, beyond just simple chat and answering individual questions, to really utilize these models to approximate reasoning, to have multiple models working together, that context window becomes increasingly important. Now, the next thing we'll talk about in terms of scale is why are we continuing to chase this? Why do we want to get to a trillion weight model? Now, if you have not seen this resource before, this is from epicai.org, and it is a fantastic resource. If you want to know anything, and I really mean almost if not any bit of information about how large language models and AI are evolving at a global scale, epic.ai is a fantastic resource for you. Now, what this graph is a graph over the last about 10 years of Epic AI's capabilities capabilities index. And this is a variety of tests. Some are mathematical, some are engineering, some are more general knowledge tests, but subjecting the large language models to increasingly sophisticated tests. And you can see over this period, there's a fairly linear growth here. But remember, this linear growth has been powered by increasing order of magnitude on the number of parameters inside these models, and also when we increase models by an order of magnitude in parameters, we increase their resource utilization by 2 orders of magnitude. So what we're really looking here is a pretty impressive resource consumption scaling graph. Now, just so everyone has some more context, as we look to the upper right of these graphs, you can see several of the global players who are participating in this development cycle. Every one of those dots on the upper right represents hundreds of millions of dollars of investment in the capital cost to run the training regimes in order to create these models. And each one of those lines, each one of these global competitors, that line represents billions, multiple billions of dollars, looking to scale up even farther in terms of the capital investment that they need to make. So when they think about, building out that next gigawatt AI data center factory, they're thinking about billion-dollar and multi-billion-dollar investment. So tremendous opportunity, absolutely, but also at a tremendous cost, both operational and capital. But this is the motivation. We are still seeing improvements in the capabilities as we increase these models, even though we are realizing we are paying a quadratic scaling price. Can we go to the next slide, please? Thank you. So I just wanted to get people again to be calibrated on the kind of societal impact and the kind of engineering that we are needing to perform to do these kinds of systems. So here are the 3 exascale systems from the U.S. Department of Energy. So HPE has been the provider and integrator of these systems, delivered in over the last 3 years. And you can see we measure these systems in tens of megawatts, from 22 to 30 megawatts. As a calibration point, an average U.S. residential customer is 1.2 kilowatts. And that means that the entire Department of Energy exascale computing platform is the equivalent of 76,000 U.S. homes. Already a sobering number. We have to be thinking about that. We have to plan and engineer for that. Recently, the other day, I looked at the specifications for a 100,000 ampere bus bar to deliver 800 volt DC into a modular data center consisting of 400 kilowatt racks. So these are the kind of numbers we're going to talk about. But let's go to the next slide. And that is, as we think about, again, we hear this term gigawatt data center. You might have seen the news a couple weeks ago an announcement of potential collaboration between OpenAI and AMD, and the number of the way that they specified the deal wasn't the number of chips, wasn't the number of wafers, wasn't the number of sockets or anything like that. It was specified in gigawatts. It was specified as a 6 gigawatt. So the gigawatt data center campuses are coming. We've seen some footprints that are, approaching the size of the Isle of Manhattan. So these are massive, national works. And again, to calibrate everyone, understanding how we will prepare and engineer energy delivery systems that are capable of maintaining and providing for these systems, because 1 gigawatt AI factory, again, 1.2 kilowatts versus 1 gigawatt, that's 833,000 U.S. homes. That 6 gigawatt deal, 5 million U.S. homes. And when we think about that, we also have to remind ourselves there are 750 million people in the world with zero access to reliable electrical power. So these are important for us to understand all of the energy and engineering ramifications of the scale of system. This is now not only a matter of engineering and engineering at every scale, again, down to understanding the leakage and the energy energy density, especially of individual transistors, especially as we look to scale and to go into 3D scaling in logic devices. I know we've already had it for memory devices, but as we talk about logic devices, especially throughput logic devices, and that's what these GPUs are now, incredible throughput systems where there isn't any dark silicon anymore. It's all in continuous use. It all wants to begin to return the investment on this energy, on that capital and operational costs. And that's why this becomes not just engineering, this becomes policy. And there's certainly around the world, nations and regions are beginning to struggle with how do we solve the policy discussion, that interplay between massive private point resources and whether that's point generation, a small modular reactor, a gas turbine right adjacent to the gigawatt data center AI factory, knowing also that we have private distributed small scale and large scale resources, and we still have the public grid, and it has to be a part of this equation, but it won't be perhaps the dominant factor as it has been in the past. So all of this is pointing to the need to have that holistic co-design conversation, up and down the stack, all the way down to the individual devices, all the way up to a national energy and AI utilization policy. So we can go to the next slide. I believe this is my last one. So we want to think about this, especially, as much as we've seen the impressive results. You look at that OpenAI, that Epic.ai, that capability graph, and we see that increasing performance of these systems now engineered at the gigawatt AI factory scale. We want to remind ourselves that this is just the current waypoint, and what we really want to look at here is this drive towards, I'm sure many of you have heard this term, and maybe you haven't really thought about it or seen a solid definition, but agentic AI. And this is really the confluence of these three streams we see coming together. AI started out as modeling, computer-aided vision. Hot dog, not hot dog, was the old joke that you might have seen the Silicon Valley comedy. But as we move from that initial decision making to reinforcement learning, beginning to adapt towards specific problems, then we added generative AI, that ability to digest and create models encompassing pretty much everything we've ever recorded to digital media as a species, and to be able to predict token after token across multiple modalities of output, text, image, sound, audio, all those things coming together to create those foundational models. But then when we use them for agentic, we're connecting multiple of these collaborative models together, connecting them with enterprise data, connecting them with additional computational sensor and actuation resources, and then giving them a job, giving them important jobs in control systems, in enterprise decision-making systems. That interplay is there, and that is where we need to begin to think about what is it going to be like. And this might be where we actually see some of form of relief, because what is coming together isn't just a single model with a trillion weights, but perhaps a whole cadre of smaller, more sophisticated, more focused models, and understanding how these models cooperate together. At the same time, we have to remind ourselves of the data, both the data coming in the beginning of the process to train systems, and then again at the end of the process to provide the input into those inferencing engines. And what has been powering this today has been the increasing capability of accelerators and GPUs. As we look forward, we might see, bringing in novel compute, but part of the challenge we have right now is all of these things are moving so incredibly fast. 2 weeks ago, we had the NeurIPS conference in San Diego, California, probably the premier global AI academic research conference. And it is, certainly the assumption these days that technology is leaping directly from those conferences directly into global production. There's so much opportunity that we're seeing papers, almost immediately being put into. There's somewhere, a private wealth fund, a $1 trillion capitalized enterprise really pulling these things directly into production. And that means that the semiconductor design cycle, the 2 to 3 year design cycle, that ability for us to do really great energy efficient designs, unfortunately at this point may not be in play yet. But as we see the real enterprise and agentic applications emerge, as we move beyond the initial evocative, amazing evocative demonstrations to actually reducing this to enterprise practice, that is where we might see the ability of the semiconductor design community to build full force, not only of the traditional design methodologies, but now using AI in the power of generation of next generation semiconductors in order to make them more efficient, and more efficient not only in the energy, but more efficient in the time to solution for a highly specialized, highly functional design, specifically designed for some of these applications. So we think about all that. The last thing we'll say on this slide is all of this is a combination of all of our resources. It is computation, absolutely, but it also is a massive amount of data movement. So it is networking and photonics and electronic networking. It is also a lot of data storage. So all of those elements coming together, testing us as we've never been before, but that is certainly setting up huge opportunities for us as a global community. But just be prepared for some eye-watering numbers, for some very challenging problems. But that's what was so powerful about the community we've collected together in the conversation we're having today. How do we look forward in a couple years when we'll be able to intercept some of these technologies, even though they are advancing so quickly? Thank you.
Thank you, Kirk. This was really interesting insight on how the models are evolving and the impact on the energy demand. Just one question I would like to ask you is that this graph clearly shows the progress in the number of parameters over last 3 years, and that has already shown where the industry needs to head in terms of data capacity and energy consumption. So what are your thoughts on the next 5 years in terms of modeling these models getting more complex, more parameters? And do you think it will be more about creating energy infrastructure, or it will be more about energy efficiency part that will come into play?
And I think, and just be clear, this is this graph is the graph of the capabilities of the model. That would have been a good thing to overlay the parameter count. Now, what we saw in the beginning on the left half of this graph, it was order of magnitude parameter increase every single time. Towards the end, things were starting to flatten out a little bit on the number of parameters. And what instead people were doing was driving more and more training data into a smaller number of parameters. So we're seeing a little bit of a flattening on the parameter curve, but the anticipation is that there's no reason for it to not begin to continue to increase again. So that is sort of the open question. But what the real interesting question is as enterprise begins to evaluate particular fitness for use, and this is where that agentic model, where we take multiple large language models, use them for together and have that interplay. So you probably have heard about MCP, the way that models are communicating together, and we're connecting those models to massive pools of enterprise data, to massive enterprise sensor fleets and actuation fleets. And that is where we might see that flattening back out to smaller, some people have even heard small language models. So there might be something where we see a pullback on the model size and then employ, sometimes you might have heard it called mixture of experts, having multiple models, multiple smaller models, and they're acting in concert. So you have one model that is the what if portion of a problem. We'll have another one that is the critique portion of the problem. We'll have another one that is the optimization portion. And then they might be invoking simulations. They might be connected up to digital twins of complex economic or physical, cyber physical systems. So I think it is certainly is an open question how models will continue to improve. Certainly, there are some important leaders in the field. Yann LeCun, lately of Meta, now striking out on his own. You know, he has been saying for quite some time, if you want to work towards artificial general intelligence, stop working on LLMs. Use a world model, use some other alternative techniques, and I think that will certainly be an open opportunity for us. And why, you know, it is certainly we should be evaluating, but we should always have understanding that there is risk in snapping to any particular model or approach right now because the field is so emerging and dynamic. And given that even on a, with a crackerjack team, from inception to high quality yield on a cutting edge design node for a large ASIC. In this case, it's not just a large ASIC; it is multiple large ASICs on a 2.5D integrated substrate. That's a tough job, and it's like a 2 year to 3 year job, even with a world class team. In 2 to 3 years, are we going to see something different? And that's why we might be paying that energy and integration cost right now, just because we want to make progress, but nothing has settled out yet, and we do need to be playing off perfect, great, provably optimal efficiency versus a little bit of agility, and that's where we find ourselves now.
Okay. Thank you, Kirk. This was really insightful conversation and presentation from your side on this agentic AI and workload. And I would like to invite Paolo for the presentation. So Paolo, if you can share your screen.
Can you see it?
Yes, we can see the screen.
Okay. Let me go to presentation mode. Okay.
Yes, it's very clear. Thank you.
Great. Thank you. So, good day, ladies and gentlemen. I want to show you today how this amazing AI technology came together. The first rule to remember is that, that most of the inventions of the future come from something that was developed way in the past. And in the case of AI, this is precisely what has happened. Now, AI had been around from the 30s, essentially with Alan Turing, but for 70 years, nothing happened. So why all of a sudden this technology became so relevant? And the reason is the completely unintended technology, 5 of them that have been developed for completely different purposes, came together. The first one is the GPU. The GPUs were developed for a very specific reason, to build games. So, the point was to make images that were extremely good and exciting. And to do so, however, they had to process a lot of pixels in parallel. Now, if you look at another definition related to artificial intelligence, it says that by definition that it wants to process a gigantic amount of data in parallel. So you can see the word parallel appears in both cases, but the two are completely unrelated to each other. So it takes the fresh mind of students to put one and one together. And so in 2009, the student at Stanford utilized some GPUs that were built to make graphics, and realized that they could process some AI algorithms. Now, the key moment, 1980, the PC was formed, 2007, the iPhone, and I put at 2009 the key point because this relation began. Essentially, Professor Bill Dolly, that was in charge of the computer department, realized that actually this was the beginning of AI, and Jensen Huang was making games. So at that point, he's extremely articulate nowadays, but he didn't know anything about AI. So where was NVIDIA at that time? It was number 21. Essentially, it was a $3-4 billion unknown company. And however, 10 years go by, and here we come in 2018, the VLSI Symposium, And I was in the third row, and Bill is presenting and say that finally he has put it all together, has designed ground up the perfect GPU for AI. And this, in the meantime, Jensen had 10 years to learn and prepare. And this was really the beginning of proliferation of this. So at the end of the talk, I went up to Bill and asked him for one slide that he very kindly let me use. And you can see in this, this part is the traditional CPU that after performance, that after 2004, when the power limits were reached, had declined. And you can see instead this AI accelerator that are continuing as in the past or even better. And you can see in 10 years from number 21, NVIDIA jumped to number 8. Now, this announcement that was in the technical community should have spread in the next year or two to the larger community of the consumer and begin to realize what was happening. But the consumer were busy with something else. Essentially, the pandemic took the attention of everybody away from this subject, and actually was beneficial because it gave the AI community 4 years from 2018 to 2022 to really prepare. So that when the AI finally reached the consumer, it came out with the bang. And in fact, you can see with ChatGPT was popularized, in 2 months reached the 100 million users that it had taken years or months for the previous technology. So finally, the age of AI had arrived. Now, who made this age of AI work was finally a ground up, GPU that, as I said, is completely misnamed. You should call him AI accelerator. But, when you have a brand name, don't leave it. That would be very bad for the publicity of the company. And you can see it has 144 streaming processor. Each one of them has additional multiple CUDA processor and so forth. But the point is, this could have been the best day and also the last day of AI, because this die, that had 80 billion transistor, have reached 114 millimeters square. That was essentially at the limit of what the scanner can do. So it means nothing else could have been done. So 2022, designing for the next technology, what are we going to do next? And so this is the number 2 technology. It's called C4. That is not an explosive, even though it has the same name, and it relates to the assembly world. If you have a package, this has as many pins as you can put on the side. And how would you assemble all these elements? The technology was very simple. If you were assembling something on the board, you would have a wire like this. I used to make a transistor radio. That's what I use. There was like 60-40, thin lead, and then a hot tip, and that's how you would solder the different components on the board. So what IBM did, wanted to go from this die size up technology to something that could have a much larger number of outputs, and so deposited this thin lead into the bond paths, and then the only thing you had to do is had to flip the chip to assemble it. And you can see this is a vision to the right of what came out of this technology. And you can see the number got essentially, 3-4x. Now, in the 80s, Intel and IBM had technology exchanges. And actually, I was in the group that went to IBM for this technology exchange. So we decided at the time, even though we didn't know when we were going to use it, to have this technology. And so we transferred this technology. And actually, in 1992, we realized, a test bed. Essentially, you can see the rectangular, 486. Then you can see several dynamic RAM, a static RAM, a voltage regulator. All of these were quite different from the IBM concept, were essentially taking a heterogeneous integration of components. But the main point was that all of this was assembled on a silicon substrate with multi-layer interconnection that connected all these components. Nothing happened, was very expensive. SoC, system in chip, was progressing well. We put it in the garage and say, maybe one day, a few decades from now, we can use this technology. And so 2 years later, the challenge of Blackwell was, how do you go from 80 billion to more than 200 billion when you cannot increase the die size? And so this, as I said, it was time to go into the garage and pull out this technology. And the only difference was that lead was recognized as harmful to your health, so it had been changed by bismuth, but essentially this was the IBM technology. And so in this case, all you had to do, you take the two dies and then there is a small silicon chip, and through this you can connect the two die, and people say fusing the two dies, is a nomenclature, but that's not what we're doing. And so with this, Blackwell arrived. You can see on the left-hand side the two die that are fused together. And then a couple of these and Grace, the CPU, are put on a board. And so all the elements necessary for this technology were 100% available. So the technology to put together, the different die was available. And like Kirk was saying, the amount of memory that is needed is endless. And all the technology, vias, pillars, all of this available to put together the memory. And you can see here, how the processor, the GPU, is connecting to all the different memories on this interposer. So what comes next? So given that we gotten from 1 to 2, it was easy for me to make a forecast that the number of dies that are interconnected will increase. This was the beginning of this year. And indeed, 3 months later, Rubin Ultra was announced, and look and behold, from 2 radicals went to 4 radicals. And so it's easy to make a forecast of what will happen likely next, then 2, 4, most likely Feynman will be probably 8 radicals. So this system can go on for quite some time. Now, the second element is water cooling. This also is an old technology. You can imagine with 1.3 kilowatts, the amount of power that is used in this case, the die of the Blackwell will run really hot. And fortunately, in this case, IBM had already pioneered this technology as far back again in the 60s. And they realized that to cool down the die, they had to use water cooling. Now, they had a lot of failures. So essentially, there was a plumber or standby because they had a lot of leaks. This continued with the supercomputer. As long as they were using bipolar, that's the only thing they could do. And then in the mid-90s, there was the switch to CMOS that consumes much less power. And so the cooling was limited to fans at that point. The technology, as you can see, that IBM had put together was very crude at the time, functional, but quite crude, I would say, because you really essentially had a bronze spring-loaded top that would push on the die, and for good thermal conductivity, and then you would have the water channel here. You can see the water channel and the metal plates right here. So look at the image on the left, and the image that you have with the Blackwell is precisely the same kind of image, and that's precisely what the industry has done. And then, if you look at the board, then in this case, in each board, you have this arrangement that I showed you before. And so altogether, you put multiple trays together, you put a rack together, and the outcome is the following. You have 10 and then 18 trays with Blackwell. And then you look at the power, 130 kilowatts for a single rack, and it's keep going up. And then you have the communication links, and then you have all the different cooling that is done in the data center. This major transformation, as I said, data center used to be warm, but they use fans. There is another technology, this is even stranger yet, MRM, that is coming up now. Now, the connectivity among the GPUs is incredible. This is an example from one of the presentations from Bill, and says that it takes 20 GPUs just to download a copy of GPT-4. So all of these had to operate as if they were a single GPU. So immediately say, okay, you want the ultimate connectivity, has to be fiber optics. So the typical CPU data center already had connection from one rack to the other, and about 2.3 megawatts, this is from the NVIDIA presentation, were used. But in this case, now you have to connect all the boards in a rack, and you want to also connect GPUs in the same board. And so the calculation says about 40 megawatts. Now, this equivalent, give or take, to 200 racks. So, it's a gigantic price to pay. Now, the technology comes from a world that most of you didn't experience. It comes from the ring modulator. These were invented in the 60s and 70s, and for science fiction. Essentially, you can see if you have a wave and you superimpose it with another wave, you still retain the key element of the initial wave of the sound, but the sound is distorted. So in science fiction movies like Forbidden Planet and so forth, you could get this sound by superimposing these two different frequencies. In fact, it was very popular. You can see it was used, if you can see here, you see different wave function, sinusoidal, square, and so forth. And progressively from the ring modulator became the ring module. And for those in the 60s or 70s, to have a good module was to have a good feeling. And you could connect this to your electric guitar and produce sounds that the guitar would never imagine to perform. So what does it have to do with AI? Well, the point is that you're going to do something very similar at this point. You have an optical waveguide, and then you have a ring. Now, as you can imagine, the relation between geometry and electromagnetic wave is such that the frequency that can only, the only frequency that can survive in here is related to the radius of this ring and to the index of refraction because it's in the media. So this is the basic wave. Now, how can you modulate this? Well, if you change, you can see here, apply some voltage, you change the concentration of either charges, negative or positive, it changes the index of refraction, then it changes the frequency, and you can see to the right, this is the real thing, okay? So NVIDIA has announced that they will put this into manufacturing, is already in the 3 nanometer line of TSMC. And this is my back of the envelope, so this is not NVIDIA. My estimate that these 40 megawatts can be reduced to the range of 4 megawatts or even less. We'll see. I'm expecting an announcement in the first quarter about this. The fifth technology that comes away from the past is wafer level integration. It's not coming yet, but it will come soon. Gene Amdahl was a legendary architect. And in 1979, he formed a company called Trilogy with the idea of creating wafer scale integration. That is, the whole computer on a wafer. The idea was great. Unfortunately, this is the best picture I could get of the wafer. It's not very good. But you can see on the wafer there was going to be an array of interconnected processor. However, the yield in the 70s was about 20, 30, 40% at best. So it failed due to technical limitation. The manufacturing yields were very low. Packaging technology was not available, and the cooling, was incredible. It was not really effective at the point. But now what happens now? After another 4 years. Now, I'm not saying that this is the implementation, but this is perfectly doable. The typical yield on a line is 90%. Means, if you have like 65 dies, 60 will be functional. So it's perfectly adequate. But I went through the different patents and I saw this that is quite interesting. That was not the end of the game. Then you could take multiple wafer, that you cut in a square, and connect them together. So we gone from transistor to make SoC, to die, to make SiP, and now you got to full wafer to make the next phase. And you can see that the SMC already understand this because the size of the substrate that is increasing, but in April they show that the next one is going to be this kind of size where the whole wafer represents really a system. So, then I can make the last forecast of 2025 and say that the number of wafers will at least double with every new generation when you can stack multiple wafers in this way. So let me come to the conclusion that all of this has created an incredible amount of wealth for the companies that are involved in this. Consider that while the best processor could sell for $5,000, now you can sell the GPUs for $50,000, $60,000, $70,000, to the point that Jensen Huang calls a rack at $3 million the basic ingredient. And what will happen this year, for the first time in history, a fabless company will be the number one for the semiconductor industry. So let me come to the end. Isaac Newton said, if I have seen further, it's because I use old technology. I was riding on the shoulder of giant. And what I showed you after 350 years, all the 5 technology already existed. But he said that people remember images more than anything else. So I want to leave you with the last slide of an image. And this here, it make you understand how AI is riding on the shoulder of giants. Okay, thank you very much.
Thank you, Paolo. Interesting video at the end. I could not say whether it's real or generated by the same AI solutions, but
you can see AI riding on the shoulder of giants, right?
yeah. Okay, just one short question, which is also coming from the our attendees. So you have you showed about the market share, and all these companies are mainly the established companies. Do you see that in the next 5 years there will be a startup emerging company who might end up replacing or challenging these based on how the progress is going?
The best thing a startup can do is to be acquired, because the size of this company, the size of the investments is so large. Thinking that a company with even investment of 100 million could reach the scale necessary, even if it's very valuable, is very unlikely. So I think the big players, essentially, if I say for the components, TSMC and NVIDIA provide the components. They have replaced the Intel, Microsoft of the PC age. And then, company like Microsoft and Google will provide, a lot of the, infrastructure. And then you have Amazon that will deliver the goods directly to the people. So this company is a size that it cannot be reached in few years. So AI startups are valuable. The best they can do is to be acquired because there is not enough time, to grow at the rate that these companies will grow.
Okay. Thank you, Paolo. I appreciate your insight on this topic. And now we will move to the next presentation by Mustafa, Director of Engineering at Qualcomm. Mustafa, I would like to invite you to share your screen and your slide deck.
Sure. I think Chetan, you have to stop sharing, or Paolo.
Paolo, you will have to stop sharing. Thank you.
Okay.
Mustafa, you can go ahead.
Thanks, Paolo.
Yeah, we can see the screen, Mustafa.
Perfect. Good morning, everyone. I'm Mustafa Badaroglu, Director of Engineering at Qualcomm, also working as Mormur IFT Chair at IEEE IRDS. I'm going to walk through some technological aspects which drives AI, and as well as some basically system level solutions augmented by technology solutions. So if you look at the essence of AI today is not only on data center, but it's everywhere. So from variables, from mobile, from automotive, from AI PC, all the way to the system interconnect backbone, so which is also AI augmented, and then the high performance computing, general purpose AI happening at the data center. So the use case of AI and the edge is bringing basically interfaces that user is not anymore thinking that it's really interfacing with the computer or mobile phone, but rather mobile phone and computer trying to understand what the user is doing. And then basically, instead of learning how to use computer is making it more attractive for the user to learn about the user himself. And the cloud computing is more general purpose AI, basically augmentation of all cognitive functions, and then enhanced for basically providing abundant computing and employing advanced packaging and cooling solutions for scaling up. So the AI is mostly today, the bottleneck is the memory, and also the temperature and footprint, how to bring the compute efficiency at unit temperature and area, and also how to increase the memory bandwidth and memory capacity and scale it up and scale out. So the advanced technology insertion points in that space for AI is from IoT all the way to variables, and then PC, mobile, and high performance computing. So this is actually, we are back to the era of parallelism. So this is really good news for semiconductor industry. The more dice we have, the more max we have, the more compute performance. So we are not anymore actually limited by frequency scaling. So we call this era is the spatial computing, where computing can be distributed everywhere, including the interconnect backbone. So the DRAM memory bandwidth and compute needs for generative AI is booming, and market forecast is reaching beyond 2030 above $1.4 trillion. And if you look at the all technological investment that we do for everything globally, 12% of the technology spending will be done only in generative AI. So the time to market is also an important driver. Technologies are changing abruptly, and but how to bring the technologies onto the user at a 6 months cadence, at 1 year cadence is very, very crucial to take maximum advantage of this semiconductor volume increase, and then dense pitch chiplet integration is becoming a more driving force for time to market, and also yield considerations for how to tackle the large die sizes and enabling faster yield ramp, bringing product short amount of time, and 2.5 to 3D integration, especially for small factor and different technology bonding, is getting very, very critical. On the other hand, we have to handling the process complexity, new materials, and advanced packaging, particularly for bringing more compute and memory and bandwidth solution, as well as how to deal with more process steps and not enabling us to measure the known good die very effectively. And then this is bringing redundancy everywhere and fault-tolerant computing everywhere on compute, memory, and I/O fabrics. So if we look at the AI workload, now we see basically this graph can explain what is needed. We need more memory bandwidth, particularly for AI inference application, where x-axis is showing basically amount of memory data needed for making one computation. So basically, it's showing the memory reuse in the compute function. And then y-axis is showing the teraflops that you can achieve. So most of the AI inference applications actually lie in this part of the plot where we have to really increase the memory bandwidth if we want to increase the throughput from the system. So for high batch inference systems, which is typically well suited for AI data centers and as well as AI training, it will require more compute resources because you are able to reuse the same memory for multiple users or multiple batch size workloads that can be actually limiting the performance directly limited by the compute. But here, advanced packaging for both are the primary solutions actually making this is achievable. Advanced packaging for the first part of the graph providing high bandwidth and more providing high memory capacity by simply number of bits for unit volume scaling. And then for the compute bound, particularly low energy and efficient power distribution network, advanced packaging is key. And more for compute capacity and efficiency, putting and integrating more max, maybe at wafer scale, as Paolo addressed in the previous talk. So basically, if we look at why do we have this memory gap is there are 4 reasons. One is the power wall. So to get the data from the memory, we really spend 2 to 3 orders of magnitude energy just for 1 bit of the data to be transferred to the compute. And then compute area efficiency scaling far better than the basically I/O bandwidth scaling. And that's also a primary bottleneck. And also now new workload models dictating less DRAM data use that we need to fetch the DRAM data more. And to make it basically the gap much more becoming a problem for us. And then also the interconnect on the package, particularly resistive and lossy interconnect, we need improvements to provide better latency for the system. STCO mitigation is basically primarily addressing this, bringing compute to the near memory or in-memory computing, increasing memory bandwidth through advanced packaging, particularly addressing the number 2, and also novel data formats, for instance, reducing resolution like scaled FP4 floating point 4-bit formats, and large cache integration, novel SoC fabrics, which is addressing the DRAM data use by increasing the cache size on the compute. And then finally, low resistance and low lossy interconnect technology, addressing the low latency. Unfortunately, advanced technology is not helping on the low resistance. That's why we need a boost by advanced packaging or other type of backside interconnect fabric to provide the low resistance routing for long-distance interconnect. If we look at the two complementing technology routes for system scaling, more scaling, basically advancing the device. Now we have lateral gate-around technology, which we expect to have a 1 decade dominance of this technology, primarily using the same device, now stacking the different device tiers on top of each other, like PMOS, NMOS on top of each other, or stacking these tiers also with just local interconnect between, bringing the 3D VLSI era for the second decade of this. And then this technology cannot survive without advanced packaging. And advanced packaging basically bringing these devices, first of all, making device compatible for the packaging, and then such that we can do advanced integration these days, 3D memory and logic, enabled by dense pitch via and dense RDL technology, bringing more backside functions for clocking, for power distribution network, and long bus routing, and then domain-specific chiplets, which can be also wafer scale, integrating a fully functional wafer or very large interposer, putting all these elements, particle connectivity, power distribution, and it can also be memory and as well as optical at wafer scale. So this is this is the device architecture evolution where next decade era through functional partitioning with fine pitch via that will enable 3D VLSI right after lateral gate-all-around technology. This is the key metrics actually we have derived from the IRDS projection. So we don't have any problem in the compute performance improvement. So we expect to see with the given of the scaling and adoption of the 3D stacking technologies and more regularity and fault tolerance, we expect to see 25x increase of the performance, and even at the performance density at unit area, about more than 400 at 15 years that we see as the forecast. But the real problem is the power density. So the power density is expected to increase about 5x, and this is bringing a lot of issues for aggregate power increase, as well as the thermal solutions dictating the performance scaling being stopped because of the power limits, as well as the aggregate power delivery limits to the system. And then this is basically addressing why we have better performance scaling, that we are around, for an inference chip, around 128K max, and then we expect to see a significant increase in the number of MAC units in a typical SoC for even for a mobile SoC to reach a significant number of MAC counts in the system. The aggregate power and the cooling is the biggest problem today we face for scalability, and especially top scaling that I mentioned in the earlier slide. Cooling solution is key, and now data center is now not anymore thinking electrical conduction, but also different type of conductors. How to bring liquid channels even at micro level, increase the flow rate of the water or any other thermally conductive liquid to basically improve the cooling thermal conductance, such that you will have better heat dissipation from the rack, and then basically putting a full infrastructure also as thinking like the system interconnect fabric, also cooling interconnect fabric is getting critical. And then other thing that we have to consider is the optical link, which is another transistor where Paolo presented as the ring modulator. Now this is going to be a new form of a transistor where This is going to be enhanced by modulation. Now we will have these three conductors that are going to happen on the chip fabric, even at the micro scale and the nanoscale at the electrical level. So the electrical, liquid, and optical being happening all three at the same time. But the power problem is not solved yet. So now the thinking is that creating directly, even going to a more, this is already known, applied today, immersive cooling, putting the whole AI card in a thermally conductive liquid, and also providing aggregate power with a nuclear micronuclear reactor, where this is the size of almost like quite a small reactor, but good enough for data center. But the goal is to provide a gigawatt scale power to the data center by putting this next to data center. So it's all about the gigawatt gain, and knowing the gigawatt, we know what tops we can achieve from the data center. Now data center is graded by what is the watt scale of the data center to know about performance that we can achieve from the data center. So my last slide, this is our basically our view for how to solve the power reduction problem, and also bringing more use cases for AI is basically disaggregation and heterogeneity. So disaggregation can be done in the interconnect backbone from edge AI with intelligent and high bandwidth connectivity to edge cloud and far clouds, enabling this system. And then more and more AI use cases are getting mainstream, and a lot of localization of the data, and requiring a lot of low latency, such as autonomous driving and more user experience for digital cockpit in the car, humanoid robots that is actually coming into the consumer scale. And this is basically a lot of use cases of the multimodal AI, where different modes of AI has to be very connected with very low latency with directly local data generated. So to enable this, we need higher memory bandwidth at AI scale, and then near memory computing with SoC, and also different heterogeneity in the memory architecture necessary to enable this type of different workloads map into multimodal environment. And then in terms of the data center, now data centers has been already be disaggregated and being disaggregated further and further, because there is no, for the workload, there is no one unique homogeneous data center that can handle things efficiently, and the GPU utilization cannot be efficient, or memory utilization cannot be efficient. Some of the functions, as I mentioned, can be memory bounded and compute bounded. Encode, prefill, and decode for a large language model can be segmented in different data centers, and are creating different pools of compute bounded and memory pools and compute pools connected with a connectivity fabric, which is basically depending on the type of the workload, whether the network latency more important, or memory bandwidth, or compute. You see that some of the solutions doesn't require memory bandwidth, but more compute bandwidth. This disaggregation will further optimize the total cost of ownership, as well as the power delivered to the data center. So disaggregation, like we did in the past, bringing domain-specific accelerators to the system and package, and also heterogeneous computing on the SoC. This will happen in the complete backbone of the globe with fully connected AI, and distributed computing is the key to solve the power crisis that we face today. That's it on my side. Thank you so much.
Thank you, Mustafa. This was really insightful details on both on the edge side and also on the data center side, because that's how the training and inference is going to go over the next few years. Just one question, taking it from the audience also, that So you talked about the packaging solutions and also the gate level advancement. So do you see this a specific part, like say packaging works on the data center side and the gate level will work on the edge side or the mobile side of it? So how do you see this solution going forward, and which area will adapt which type of solution compared to packaging or scaling?
Yeah. On the consumer side, on the edge AI, cost is very, very important. So particularly, it's not that easy to do disaggregation because every consumer has one chip. Advanced packaging solution is key, particularly for disaggregations of some of the SoC functions like power distribution network or getting the scale compute disaggregated from the I/O solution, and also enablement of the near memory computing, particularly bringing memory bandwidth to edge AI, which is the fabric that is listed here. And also, since the wafer prices are increasing a lot, this disaggregation at the system and package level will help for cost to reduce at the edge AI space. On the data center side, it's mostly performance and cooling driven. Total cost of ownership is mostly on the algorithm innovation and more disaggregation optimization. But to get the cooling and the high performance advantage, advanced packaging is key. And without that, actually, there is no scaling for HPC if there is no improvement in advanced packaging. And also, advanced packaging has to be also made compatible with system connectivity fabric, like optical as well as different type of cooling solutions integrated as part of the package framework is so important for high performance computing related advanced packagings to work out.
Okay. Thank you, Mustafa. And we are nearing the end of this panel session, and I would like to thank again Kirk, Paolo, and Mustafa for spending time with us and sharing the insight on the AI semiconductor and how the technology has advanced from decades ago to future. Paolo, if you have any parting thoughts before I conclude.
I'd like to say that all these subjects are discussed monthly, in the IRDS. So expect a lot of additional, presentation and information next year. This was just the baseline, but each one of these subjects by itself, would have taken the full hour. So this was like a menu to give you an idea. We didn't go into the excruciating details. But I hope next year we can have some other webinars when we address one by one all these subjects in great details. So it's an exciting time. And the main thing that I want to conclude is this is not the .com. This time is real business. The .com were companies that didn't have a business plan. Pet.com realized that they were delivering dog food for $5, and it costed $5 to the guy that would deliver the food. So it was insane. But this time you have the big guys, companies that are worth hundreds of billions, market value of trillions. So they're really engaged in changing the situation. The consumer can enjoy all the side benefits, but the real customers are the corporation. This is a game of corporation to corporation, and I would like to spend time with my colleagues next year to explain how this is going to play. Thank you.
Okay. Thank you, Paolo, and really looking forward to next year and the next decade on this front. And as a final thoughts, I would like to thank IEEE Future Directions and IEEE Global Semiconductors Committee and to sponsor this event. And thank you to all the attendees who made it today. And this presentation will also be on the on-demand section, and Ipshita has already shared the link on the chat window. So hopefully you will find it interesting and you can always visit this on an on-demand webinar. And thank you again, Kirk and Mustafa, for your time. Really appreciate it.
Thank you, Chetan. Thank you.
Thank you, everyone.
Mustafa, Kirk.
Bye.
Bye-bye.